On workday one for the potato cannon, we were focused on working on the ignition system and specifically the spark, since that the spark was going to light our fuel. While looking at the sparking system, we ran into some kinks. The angle of the screws, how conductive the screws were, or if there was maybe a better conductor to use, and the wattage of our actual sparker. We were using little sparkers, I think, for grill lighters, and they just weren't very consistent, which was another issue we ran into, consistency that we were trying to work on and correct. Through our trial and error and just solutions we were working on, we found that if we could up the wattage, it would create a more consistent spark. Also, the spark would reach a farther distance and work better, possibly. And changing the angle, like in the picture here, when the screws were angled on different planes, it didn't spark as well. But when you put them on the same plane, you could get a longer distance with the sparking arc and a more consistent spark with what we were using. So we really found out that if we could up the wattage, the spark would be better. If we move the screws around, the spark would be more consistent, and then possibly change the conductivity of the screws to create a better spark. In our previous knowledge, we knew what fuel we were going to use. Butane was the best, and aerosol would be the second best.
On workday 2, we continued.
On test day, we attempted again to use the steel wool ignition system. We tested a lot of different ways to make it work. We finally figured out that the steel wool had to be in contact with the copper wires, but the copper wires had to be very close together, and that gave us an efficient and consistent oxidation reaction. But when we tried to do it on actual launch tests, it still would not ignite the propellant. We weren't sure if that was because of the propellant aerosol actually coating the steel wool itself and preventing it from oxidizing, or if it just wasn't a high enough temperature or a strong enough spark. We still aren't sure. Eventually, we decided to use an available grill lighter that was we found on one of the test material tables. And we used screws securing copper wiring that extended into the potato cannon canister, and it gave us a good, consistent spark. For propellants, we used right guard and butane, and we got 2 successful launches. The first and the second we both timed. And as far as our results are concerned, the right guard flight time gave us 6 seconds, but that's taking into account that the potato broke in half mid-flight, and that was the time in which the first piece hit the ground. If the potato had not broken apart, it probably would have flown a lot farther. The butane flight time was 6.6 seconds. So those are our results. So how does this all translate into the classroom, and what have we learned? Really, what can be said about this project and this inquiry is that it's a very, very large synthesis of many different scientific concepts that are coming together to influence how we design our cannon and ignition system, and the way in which we can achieve a specific task and research specific topics. We really delved into different ways of controlling the static electricity and the static discharge to create a more effective spark, and also oxidation reactions with the steel wool, and how effective that was in our attempt at making that be the ignition for our propellant. We investigated the effectiveness of different propellants, right guard and butane being the two that we tested, and obviously dealing with electricity, just the idea of conduction, and also more on the physics side of this course, this would be a great way to investigate trajectory, force, and many different other physics concepts. Overall, I think it's an excellent inquiry, but it's very important to give the students goals and control to some degree the amount of variables that are involved in this task, because obviously there are a lot of different things happening at once.